Hello everyone, welcome to lecture series on functional analysis. Example of Banach space is given over here, that is C0 space in which elements are infinity tuples of xn, x2 up to so on coordinates and all my xn belonging to k, and this is true for every n. And xn is convergence to 0 as n tends to infinity in space k. So C0 is the set of all sequence in k, those sequence which are converging to 0 in k. Here is a special type of sequences, that is convergence to only point 0. So is closed vector subspace of L infinity with infinity norm, and hence we have to prove that C0 with this norm infinity is Banach space over K. So proof: clearly C0 is a subset of C is a subset of L infinity. So here C is not a complex number. Here C is the set with all sequences which are converging to any point, right? But here you say that C0 is sequences, those sequences which are converging to only 0. So C0 is a subset of C and C is a subset of L infinity. And it is easy to check that C0 is a vector subspace, vector subspace of L infinity with infinity norm. So remaining to prove is C0 with this norm is Banach space over K. So for that it is enough to check that C0 is closed in this space, because C0 is subspace of L infinity, right? So for that, take sequence xn from C0 be such that xn is converging to y. We know that, and as n tends to infinity in space L infinity norm infinity to some point y which is in L infinity, and xn is x1 to the power n comma so on xk to the power n, and this is true for every n equal to 1 to up to so on. And my point y is, you know that, y1 comma y2 comma yn so on, right? Since we here we have xn is converging to y as n tends to infinity, use definition of this, and epsilon, for given epsilon greater than 0 there exists n0 in n such that x norm infinity of xn minus y less than epsilon by 2, and this is true for every n greater than or equal to n0. So put here the value of xn and here value of y. So this is the infinity tuples of xn and infinity tuples of y element, which is less than epsilon by 2, and this is true for every n greater than or equal to n0. So subtract this 2 point, we get x1 to the power n minus y1 comma son comma xk to the power n minus yk and so on, which is less than epsilon by 2, and this is true for every n greater than or equal to n0. So use the definition of infinity norm, which is supremum of modulus of xkn minus yk over k less than epsilon by 2. This is true for every n greater than or equal to n0. Called it as equation number 1. Since xn0 is equal to x1 to the power n0 comma so on comma xk to the power n0 comma so on which is in C0. So in particular, this sequence is converges to 0 as my k tends to infinity in k. So epsilon greater than 0 there exists k0 in n such that because x k n 0 converges to 0. So infinity norm is x k n 0 minus 0, right? Infinity norm. So here is 0, so you can write it as modulus of x k n 0. Right. So here is x k n 0 less than epsilon by 2, and this is true for every k greater than or equal to k0. So modulus of yk, you can write it as modulus of yk minus xk n0 plus xk n0. xk n0 subtract and add. So use the property of modulus, we get modulus of yk minus xk n0 plus modulus of xk n0. So this is from equation 1 and this is from equation number here 2, right? So epsilon by 2 plus epsilon by 2 will give epsilon. This is true for every k greater than or equal to k0. So finally we get modulus of yk less than epsilon for every k greater than or equal to k0, as yk tends to, what does the meaning of that yk less than epsilon will give yk converges to 0, right? Will imply that yk converges to 0 as my k tends to infinity in k. So y is equal to, here we proved that yk sequence is converges to 0. So we can say that this element is in C0, because in C0, how type of element, all sequences are converges to 0. So here we can say that my element y is in C0, right? Thus, this sequence and xn converges to y as n tends to infinity, and y converges to y in C0. So C0 is closed in L infinity with this infinity norm, and C0 is a closed vector subspace of the space L infinity infinity norm. So we can say that C0 with infinity norm is a Banach space over K. Y from Elliott theorem, right? So next example is C with closed interval AB is equal to function from closed interval AB to K where function f is continuous. It means C closed interval AB is a set of all continuous functions from closed interval AB to K, right? Is a vector space over K with respect to pointwise addition and pointwise scalar multiplication of function. And the norm is a function from C closed interval AB to R, which is defined by norm of f is equal to maximum of modulus of f of t, where my t is belonging to closed interval AB, is a norm on closed interval AB, and we have to also prove that C closed interval AB with this norm is Banach space over K. So first we are going to prove this is the norm for this vector space. It means this is a norm linear space, and uh, next we have proved that also Banach space, right? So first, this space is what? Set of all continuous function from closed interval AB to filled K, right? And norm defined as norm of f is equal to maximum of modulus of f of t, and my t belonging to closed interval AB. So for proof, it is easy to check that C closed interval AB is a vector space over K with respect to pointwise addition and pointwise scalar multiplication defined as follows. So pointwise addition is if I am taking two elements from this space, but in this space elements are function. So I am taking f and g, two functions from this space, which is defined as f plus g. This is the operation for pointwise addition, right? So f plus g is a function from closed interval ab to r, which is defined by f plus g of x is equal to f of x plus g of x, and this is true for every x belonging to closed interval ab, right? Next is pointwise scalar multiplication. So for that, we have to take a scalar. So here we take alpha belonging to k scalar and take one function from this space. So f belonging to C closed interval AB, which is defined as alpha into this function f is a function from closed interval AB to R, which is defined as alpha f of t will give alpha into f of t, and this is true for every t belonging to closed interval AB. So the zero element of this space is zero function, right? Is the zero function, and which is a zero function from closed interval AB to R. It means if I am taking any element from this interval will give always to 0. That means if I am taking function f from belonging to C closed interval AB, right? If I am applying, suppose t belonging to closed interval AB. If I am apply f of t and my f is zero function, which means any t, if I am taking any t, if I am applying zero function will give always value 0, right? You can take in any t and apply zero function will give always 0 value. So next we have to prove that this norm which is function from closed interval C into closed interval AB to R, which is defined as norm of f is equal to maximum of modulus of f of t is a norm. For that we have to prove fourth property for norm. So first property is norm of f is greater than or equal to 0. So take norm of f, use the definition of this norm, which is maximum of modulus of f of t, and t is in closed interval AB. So this value is always greater than or equal to 0 because this is greater than or equal to 0, and when you are take max, it is also uh, greater than or equal to 0, and this is true for every f in C closed interval AB space. So from this we can say that norm of f will greater than or equal to 0. So first property proved. Second property is if norm of f is 0, if and only if f is 0. So first take norm of f is 0. So if and only if, you can say that use the definition of norm, that is maximum of modulus of f of t, where t in closed interval AB is 0. When I'm saying that this maximum is 0, if each this modulus is 0, then I'm saying that this maximum is 0. So if and only if modulus of f of t is 0 for every t belonging to closed interval AB. When I'm saying that this modulus is 0, if and only if f of t is 0 for every t belonging to closed interval AB. So when I'm saying that f of t is 0, right, if function f is 0, right, earlier I have explained that when I'm saying that f of t is 0, the f is 0. So which is 0 element of this space. So second property proved. Next, third property, that is modulus of norm of alpha, which is scalar, into f is equal to, we have to prove that modulus of alpha into norm of f. So let's prove, and for that take the definition of this norm will give maximum of modulus of alpha f of t, right? So here you can split the alpha into f of t. Here we using the definition of scalar point, uh, scalar multiplication. So is equal to maximum of split the modulus will give modulus of alpha into modulus of f of t. So here maximum is only apply for function t. So you can alpha take here, will get alpha modulus of alpha into maximum of modulus of f of t, where t belong into closed interval in AB. So this is the definition of norm of f, right? So is equal to modulus of alpha into norm of f for every alpha in K and f is in C closed interval AB. So last property is norm of f plus g is equal to, use the definition of norm, that is maximum of modulus of f plus g of t and t belonging to closed interval AB. So use here pointwise addition, that is f of t plus g of t, right? Use property of modulus. So here less than or equal to and modulus f of t plus modulus of g of t. Apply this maximum to each term will give less than or equal to maximum of modulus of f of t for every t in closed interval AB, and plus maximum of uh, modulus of g of t and t belonging to closed interval AB. So this is the definition of norm of f, and this is the definition of norm of g, and this is true for every f and g belonging to C closed interval AB. So here from this fourth property we can say that this is the norm on this space, this vector space, that is C closed interval AB plus and dot. Now remaining to prove is space C closed interval AB with this norm is a Banach space over K. So for that, let Cauchy sequence in this space. So let Fn, where my n is running from 1 to infinity, be a Cauchy sequence in this space. So using the definition of Cauchy sequence will give, given epsilon greater than 0, there exists n0 in n such that norm of Fn minus Fm less than epsilon for every n and m greater than or equal to n0, right? So from here take the definition of norm, that is maximum of modulus of Fn minus Fm of t and t belonging to closed interval AB less than epsilon. This is true for every n and m greater than or equal to n0. Apply this t to both the function, will get Fn of t minus Fm of t less than epsilon, and call it as equation number 1. So we have modulus of Fn of t minus Fm of t less than epsilon for every n and m greater than or equal to n0 for every t belonging to closed interval AB. So from here we can say that this is a Cauchy sequence in K, right? And for every t belonging to closed interval AB. So this is Cauchy sequence in K. It means this sequence is converges in K, and this is true for every t belonging to closed interval AB. So define the function f from closed interval AB to K as f of t is equal to limit n tends to infinity Fn of t, right, for every t belonging to closed interval AB, and fix n greater than or equal to n0 and allowing this m as an m tends to infinity in equation number 1, we get maximum of t belonging to closed interval ab2. Right here in equation number 1 we have fn of t minus here f m of t, right? So if I'm allowing this as m tends to infinity, right? So here is the definition. If m tends to infinity of fmt will give f of t. So write here f of t less than epsilon, less than or equal to epsilon. That's why we have defined the function f from closed interval ab to r and like this. So from this you can say that fn converges to f as my n tends to infinity uniformly on closed interval ab, right? You know that what is uniformly convergent. So f is function from closed interval ab to k is continuous. If this function is uniformly continuous on convergent to this interval, we can say that this is the continuous function. Since fn is a function from closed interval ab to k is continuous function, so you can say that f is in closed interval ab. Here we have proved that f is continuous function. So when I'm saying that f is in belong to c closed interval ab, right? If f is continuous, then I'm saying that this f is in this space. So from equation number 2, we can say that norm of fn minus f is less than or equal to epsilon, and fn converges to f as n tends to infinity in space c closed interval ab and with this norm. So every cos sequence in this space is converges to with this space to some point f, where f is in c belonging c closed interval ab. So this space is Banach space over K.